Welcome to The Explainer. I am absolutely thrilled to have you here today because we are going to completely reframe how you think about space travel. We're going to tear down those old Hollywood myths and look at the absolute, undeniable math that actually powers a spacecraft. If you've ever looked up at the stars and wondered what it literally takes to navigate the cosmos, well, you're in the exact right place. Because understanding this, it's not just trivia. It is the literal difference between a multi-billion-dollar satellite pulling off a groundbreaking mission or just becoming a dead, useless piece of metal floating out in the void. So, get ready, because by the end of this, you are never going to look at a rocket launch the same way again. Section 1, the space fuel illusion. Let's move beyond the sci-fi tropes. Okay, let's dive into this. Picture it. The klaxons are blaring on the bridge of a starship, the captain is looking incredibly tense, and they turn to the engineer and shout, "How much fuel do we have?" Right? It's the classic, dramatic movie question. We've all seen it 100 times. But here is the fascinating truth. In real, actual aerospace engineering, this is entirely the wrong question to ask. If you ask a NASA engineer how much fuel is left, you aren't actually finding out what the ship can do. The real question, the only question that actually matters when you're evaluating a spacecraft's capability to survive and navigate is, what is our remaining delta V? To put this in perspective, consider the difference between 100 kilograms of traditional chemical propellant and just 10 kilograms of electric propellant like the xenon gas they use in ion drives. Now you might think, well, 100 kilograms obviously makes a ship 10 times more capable, right? But that is the illusion. Because different thrusters operate with vastly different efficiencies, both of these propellant amounts could achieve the exact same maneuver in space. The secret here lies in a metric known as specific impulse, or ISP, which basically measures how effectively an engine uses its propellant. A chemical engine throws a lot of mass out the back relatively slowly, while an electric ion thruster throws a tiny amount of mass out the back at an unbelievably high velocity. So fuel mass is incredibly deceptive. It's really not about what you have in the tank. It's about the physics of how efficiently your engine can actually utilize that mass to push you forward. Moving on to Section 2, the road trip analogy. Let's bring this rocket science down to earth. Imagine you're planning a massive cross-country road trip. The petrol in your tank? That is exactly like a spacecraft's propellant mass. But the total distance you can actually travel, that is what aerospace engineers call delta V. So the crucial point is this. Simply knowing you have 50 liters of petrol tells you almost nothing about your trip. I mean, are you driving a hyper-efficient hybrid car, or are you driving a massive, heavy-duty moving truck? A moving truck uses a massive amount of its energy just hauling its own heavy frame around, which is very much like a poorly optimized rocket. Those 50 liters are going to yield wildly different distances depending on the vehicle. And out in space, your maneuverability depends entirely on your propulsion system's efficiency, not just the sheer physical size of your fuel tank. Section 3, defining delta V, the hidden metric of the cosmos. So here's the formal definition. Delta V, represented by the Greek letter delta, meaning change, and V for velocity, is simply the change in velocity required for a maneuver. This is the absolute mathematical heartbeat of the famous Tsiolkovsky rocket equation. It's a universal measure of capability, completely regardless of your propulsion type. You see, in the frictionless vacuum of space, you don't fight air resistance. You just change your speed and direction to alter your orbit. Delta V totally levels the playing field. Whether you're using a roaring chemical rocket, a whispering ion thruster, or even a futuristic nuclear thermal engine. If an engineer knows your delta V, they know exactly what your ship can achieve. And this brilliantly illustrates our main concept, beautifully captured in this quote from aerospace engineers: think of delta V as the currency of spaceflight. I really want you to lean into this financial metaphor because it's exactly how mission planners think. You aren't just firing engines. You are opening your wallet and making literal purchases from a strictly limited budget. Every single time you fire those thrusters, you are basically swiping the spacecraft's debit card. And let me tell you, space has absolutely terrible exchange rates. Every single maneuver costs precious money from the Delta V bank. Which brings us to Section 4, the cost of spaceflight. Let's read the cosmic price list. Think of these numbers like a menu at a really expensive cosmic restaurant. Every destination has a rigid, uncompromising price tag attached to it. Just launching from Earth to low Earth orbit, or LEO, costs a staggering 9,400 meters per second of delta V. Why so much? Well, because you're fighting through the thickest part of the atmosphere and clawing your way out of maximum gravity. Getting from there up to geostationary orbit, that's another 3,900. Want to go to the moon? That'll be 3,100. Mars? About 3,600. Even just staying perfectly in place in a geostationary orbit, what they call station keeping, costs a subscription fee of 50 to 100 meters per second every single year, just to fight the uneven gravity of the Earth and the pull of the moon. And dodging space debris? That's a microtransaction of a few centimeters to meters per second. Imagine the International Space Station having to fire its thrusters, spending its precious delta V just to dodge a millimeter-sized fleck of old satellite paint. If your spacecraft lacks the currency to pay these prices, the physics of the universe will simply decline your card. Now, what's really interesting about this slide is the sheer mind-blowing scale of just getting off the Earth. Take a look at that massive bar for launch, 9,400 meters per second. It shows that the gravity well of our planet is exceptionally steep and incredibly expensive. It demands an enormous amount of energy just to reach the baseline of space. But once you've paid that massive upfront cost, it's fascinating how surprisingly cheap the rest of the solar system opens up to be. A lunar transfer is only 3,100 meters per second. There's a famous quote by science fiction author Robert Heinlein that perfectly summarizes this physics reality. He said, "Reach low Earth orbit and you're halfway to anywhere in the solar system."
Section 5. Building the mission budget. Accounting for every maneuver.
So before a spacecraft is even a physical prototype, engineers have to sit down and act like strict, unforgiving accountants using this equation, the total delta V budget. Planners have to add up the cost of the launch, the cost of raising the orbit, the years of station keeping, and the final deorbit maneuver. But look closely at that final term, margin. That safety margin is absolutely crucial, because space is inherently unpredictable. What happens if a sudden solar storm expands the Earth's atmosphere, dragging your satellite down way faster than expected? You have to pay delta V to fix it and raise your orbit back up. Every single phase of the mission must be paid for up front in this math equation before a single piece of metal is ever cut.
So why is this the very first quantity calculated? Because this abstract mathematical budget dictates literally everything physical about the ship. The required delta V determines what propulsion type you need, which then dictates your propellant mass. That tells you the size of your tanks, which sets the total spacecraft mass, and that mass tells you exactly how big of a launch vehicle rocket you have to go out and buy, and ultimately it caps your total mission lifetime. The math literally creates the machine. And this introduces what engineers call the infamous tyranny of the rocket equation. Adding even 1 extra kilogram of scientific payload cascades through this entire budget. It requires exponentially more fuel at launch just to lift that extra mass, which requires a bigger tank, which requires even more fuel. It is a ruthless, endless balancing act.
Which leads us to Section 6, when the currency runs out, the fatal reality of an empty budget.
Mass is precious, but delta V is what buys mission capability. I really want this quote to sink in. Think of a multi-million-dollar space telescope. It might have completely flawless lenses, perfect scientific instruments, and solar panels generating endless, infinite electrical power. But if it spends its very last meter per second of delta V, it is functionally obsolete. Every single time a satellite tweaks its orbit, every time a capsule docks with the space station, every time a probe swerves to avoid a micrometeorite, it permanently spends a piece of this irreplaceable currency. It is gone forever.
When that budget is totally exhausted, the realities are incredibly grim. It doesn't even matter if the onboard computers are running perfectly. Once bankrupt of delta V, the spacecraft cannot maintain its orbit against atmospheric drag. It cannot step out of the way of an incoming collision. It cannot orient itself to reach new targets. It's essentially dead in the water. And this is exactly why, when satellites run low on this currency, mission controllers must make a final vital purchase, a ticket into a graveyard orbit. They use the absolute last drops of delta V to push the satellite out of the way, into a safe, useless orbit so it doesn't become a high-speed hazard to other active missions. Once that's done, its operational life is instantly over.
Which leaves us with a profound, high-stakes question of orbital accounting. If you were a mission director staring at the telemetry screens, managing a billion-dollar machine floating out in the void, how would you spend your spacecraft's final drops of delta V? Would you push for one last risky scientific observation to unlock a secret of the universe? Or would you use it to safely bury the ship in the atmosphere to protect future generations of spaceflight? It's the ultimate cosmic budgeting decision. Thank you so much for joining me for this explainer. Keep looking up, and I'll catch you next time.